day, Calculars. Live with me today here in the studio are Mel Maramot and Neil Ahuja. But to follow some health protocols, we are maintaining a social distancing.
Good day to my co-hosts. Today is another day to help our lucky caller with his or her math problems that he or she encounters in their real world.
That's right, Mel, and for today's special episode, we have our special caller for today. He is known for being the wealthiest man in the world. VTR, take it away.
Hello Calcifix. This is Elon Musk and I am calling because I have a math problem regarding our Earth's population that correlates to population growth. I sincerely want to help the people by sharing my blessings by the year 2500. However, I need to know the growth of Earth's population in order to sum up everything so that I can keep my legacy until the year 2500. I am hoping that you can help me with this.
Differential equations have an amazing capacity to forecast what is going on in the world. They are employed in everything from biology to economics to physics, chemistry, and engineering. They may be used to represent exponential growth and decay, species population expansion, or investment return changes over time. The Malthusian law of population growth is one of the most fundamental examples of differential equations. The formula dp over dt equal rp depicts how the population p changes over time. Depending on the species, the constant r will vary. This equation was utilized by Malthus to forecast how a species will expand through time. P represents the population of any living creature and K the relative growth rate. Thus, dp over dt equals to kp. Even though human reproduction is below its biological potential, the world's human population is now undergoing exponential increase. From 1 billion people in 1800 to 7.7 billion now, the world's population has grown dramatically. The global population growth rate has slowed from 2.2% per year to 1.05% per year in the last 50 years. With that stated, let us provide Elon Musk with some realistic population growth equations.
We will now apply the Malthusian law in order to address one of the most significant challenges of our time, which is the world's population growth. We aim to know if it is possible that a population will continue to rise or if it is possible that it will plateau at some time, and if so, when. We'll look at two approaches to use differential equations to assist us in answering these problems in this section. Remember that according to one model of population growth, a population grows at a proportional pace to its size. We'll now start looking into the world's population. To begin with, we'll look at some available stats shown below on the world's population, which we'll use in our research. Our first assumption is that the population change rate is proportional to the population. This appears to be a reasonable solution. There will be fewer births and deaths if there are a limited number of people. Hence, the rate of change will be slow. There will be even more births and deaths when there are more people. Therefore, we should predict a faster rate of change. We can write this assumption as PT, where PT is the population T years after the year 2000 and expressed as dP over dt is equals to Kp, where K is a constant of proportionality. First, using a central difference, estimate the derivative of P prime of 0 from the data in the table. Assume that T is equals to 0, that represents the year 2000. P prime of 0 is equals to P of 1 minus P of negative 1 over 2 and equals to 6.159 minus 6.008 all over 2. This gives us a value of 0.0755. Next, let us determine the population P of 0. The population P of 0 is equals to 6.084. since t is equals to 0 and corresponds to the year 2000. Next, estimate the constant of proportionality k in the differential equation using the findings from the previous slide. Using dp over dt is equals to kp and the preceding values at t is equals to 0, we have 0.075 is equals to k times 6.084. The value of k now is 0.012041. We have the initial value problem now that we know the value of k. dp over dt is equals to kp and p of 0 is equals to 6.084. Find the solution to this initial value problem. So the solution for the initial value problem is pt is equals to 6.084 t raised to 0.0112041 t. Now, let us predict the population in the year 2010. The year 2010 corresponds to t is equals to 10, where p of 10 is equals to 6.8878. According to the estimate, the world's population will be around 6.888 billion in 2010. By looking at the table, the value is close to the actual population in the year 2010. Finally, let us find the population in the year 2500. The year 2500 corresponds to t is equals to 500, where p of 500 is equivalent to 3012.3. Therefore, according to the projection, the population in 2500 will be around 3012 billion, or over 3012 and 300 million people. This is an excessively significant amount for the world population.
In conclusion, one of the most fundamental instances of differential equations is the Malthusian law of population growth. Although human reproduction is well below its biological capacity, the world's human population is now undergoing exponential increase. The number of births and deaths determine the global population increase. It shows that the exponential model is more likely accurate for years to close to 2000. If we project far enough into the future, however, the model predicts increasingly enormous rates of change, causing the population to grow at an arbitrary rate. Therefore, it is illogical because the Earth's ability to sustain such a vast population is impossible. And that's a wrap for today's special episode. Thank you so much, Elon Musk, for trusting us with your problem about population growth. Once again, I am Neil Ahuja.
And I am Venice Flores, always one call away for your math problems.
And I am Mel Maramot. Stay tuned and keep subscribing to get future updates and answers from Calcifix. Bye and see you next week.